Okay, let's begin. So, I believe we're in related rates, right? So we're just going to continue, pick up where we left off. Did we only, do we do example 3? Is that the one we did? Did we get to another example? Or? I think we only did one. I might not be remembering. Okay. So, related rates continued. Kind of like this, guaranteed to be on the next test, and it will be in part 2 of the final. But it's one of the ones where I think it's not worth skipping. As long as you get these 6 steps in your head and you really you learn how to grind through them, it's actually not so bad. So the idea is, we went over this last time about related rates. It's just talking about when we have one or several quantities that are related, it turns out that their rates are related. If I know about the rates of one thing, I can figure out the rates of the other things with that relationship. So again, remember what these columns look like. So one thing is they describe a situation to you. It's usually a physical situation. So this is how you can recognize when it's a related rates problem with some related quantities and the rates of one or several are given, and you need to find the rates of another. The idea of rates tells you that the independent variable is time, right? It will always be time. They're always going to be differentiated with respect to t here. And it's a very, not necessarily are each of the steps easy to execute, but the process is simple. You literally always go through these 6 steps in this order. Right? Some of them might be done for you. So for example, as we mentioned before, I think I mentioned before, I don't remember now. Both my classes are very close together now, so I can't remember. Did I tell them this or did I not tell them this? So, one of the steps is to set up a diagram and label it properly, but the whole point of doing that is to come up with an equation in step 4. So the idea is, if you're given the equation, you can skip the whole diagram step, but it's still something that you consider. You go through these considerations in this order, and by the time you get to the end, you'll be able to solve the problem. Right? So, first step is always to read the problem very carefully, because related rates problems are word problems. And then you try to set up a diagram. You label it correctly, meaning you label what's changing with variables, you label what's not changing with constants. Write down the given information. So like I said, there will always be some information that's given that you can start off with. And then you write down what you want to find so that you don't get lost. Using step 2, or a given equation, you're going to set up an equation in step 4. You're going to differentiate with respect to t, and then you're going to pretty much plug in what you know and solve what you want to find. So that's basically the process. We went through one example, example 3. Let's actually go to example 1. Go back to example 1 now. I don't think I have any extra copies of this. If you don't have a copy of the handout, you can find it on the course webpage. But I have a couple extra copies. So let's go through example 1. So step 1, if you're going to read the problem carefully, right, to figure out what's the situation that's going on. Okay, so what? We did 1. And we did 3. Did we do 3 or did we not do 3?
We did the cylinder one. I think
You did the cylinder one, and did you do the ladder one?
Yeah.
Oh, so I did do 2. Okay, did we do 4? I don't think we did.
No.
I know. Let's go to 4. I want to do 4, 5, and 7. And then the rest you can practice on your own. So let's actually go through 4. Okay, so at noon, ship A is 80 miles west of ship B. At this time, both ships set sail. Ship A sails south at a speed of 20 miles per hour, while ship B sails north at a speed of 10 miles per hour. How fast is the distance between the two ships changing at 2 p.m. if both ships maintain constant speed? Okay, so read the problem, and now we are going to go to step 1, read the problem, right, which is describing two ships leaving from certain locations, or we want to measure the distance between them. So we kind of have an idea of what we want to do. So step 2 is now we're going to try to figure out how we're going to set this up, because we weren't given equations, so we're going to have to put them in ourselves. Right? So the situation describes ship A being 80 miles west of ship B. So that's the original location of B, that's the original location of A, and this is the length 80. Okay, so far so good. Now it says ship A sails south. So from this, it starts moving south. And it starts moving south at 20 miles per hour. Ship B sails north at 10 miles per hour. So ship B starts going up 10 miles per hour. Okay. How fast is the distance between the two ships changing at 2 p.m.? So from this picture, what would be the distance between the two ships?
80.
What?
What's the differentiate?
The what? The what? Hypotenuse of where? Where's the hypotenuse? How do you make it? What is that talking about? The distance between them? From where?
Connect the arrows.
You connect the arrows, right? This here is going to be the current position of ship B. This would be the current position of ship A. The distance between them is just a straight line connecting ship A to ship B, right? So this is the guy we actually want to find. Now, remember, it's not just important to draw a diagram, we will also want to label it. So we're going to label anything that's changing with variables, anything that's not changing with constants. So what will I label? So this length here, that's going to be constant because they're moving vertically. The horizontal distance between them is not going to change, so that's an 80 and it will always be an 80. What about this line? Is this changing?
No.
Yes, the ship is sailing. It's moving at constant speed. It's moving at 10 miles per hour. So this length is actually increasing. So this line here is actually something that's changing. I'm going to label that with a variable. Call it x.
Even with moving at the same speed?
Yes, it is moving. Right. It is moving. It's changing. Right? Whatever is changing, we're going to label with a variable. Whatever is not changing, we're label with a constant. This length is changing. Doesn't matter if it's changing at constant speed or variable speed. What about this length here? It is also changing, so I'm going to label that with another letter, y. What about this line here? It's also changing, because as each of these ships move apart, that line gets longer. So this line is also changing. Let's call that, so know that this whole thing is 80. So let's call this line Z. Okay. So that's our diagram. Step 3. What do we know? What do we want to find? We know the rate at which x is changing and the rate at which y is changing, right? So this is what?
10.
Right. B is sailing at 10 miles per hour. So I know that dx dt is 10. In fact, it is a plus 10, right, because it's increasing. This is something that you have to consider, right? Whether something is increasing or decreasing will matter in the interpretation. So it's a positive 10 because it's increasing. So we know that. What else do we know? We know how fast y is changing. That's at 20, right? So that's dy dt. It's at 20 miles per hour. It's a plus 20 for emphasis. What about dz dt?
We don't know that.
We don't know. What do we actually want to find? In fact, that's what we want to find. How fast is the distance between them changing? Z is the distance between them, so we want to know how fast Z is changing. What we want is to find dz dt. Right? We don't know what that is. I want to figure out what it is. When do we want it?
Now.
Yes. But when? When is this situation? When is at 2 p.m. So how do I describe what's going on at 2 p.m.?
From 12 to 2.
Sure. What does that mean?
2 hours.
Sure. 2 hours have passed. So what does that mean? Right. But time is not one of the variables I set up though. How can I express what's going on at 2 p.m. in terms of these variables that I already have? Yes. What? Times what by 2?
What you know.
X is 2.
X is 2.
No, multiply your dx dt and dy dt by 2. It's 2 hours.
Right. So this is a rate of change, and it's the rate of change per hour, right? From 12 to 2, 2 hours have elapsed, which means they would have moved twice that distance, right? If you're traveling at 10 miles per hour, in 2 hours you'd have traveled 20 miles. So I know that I want this when x equals 20 and when y equals 40. Right? So these are the rates I know. This is what I want to find. This is the condition under which I want to find it. So I know at the end of the day, the last thing I write must be dz dt equals some number, right? And until I get to that line, I have not finished the problem. Okay, so now the next step is to what? I need to set up an equation. Ideas on how to set up this equation. What?
What do you use that path angle thing?
How? With what variables?
With the x.
20 and 40.
So what would I say? What would the equation be?
80 squared
80
plus
squared.
x.
40 squared equals z.
How did you get that? How?
Taking the sides of the triangle.
Equals the
Okay, but the hypotenuse for this one is here. And the hypotenuse for this one is here. How did you combine them? Now do you see it? So that's what she was talking about. She looked at this big triangle here. Right? The whole length of this is x plus y, right? Because that length is x, and this length is y. The base is a, and the hypotenuse of that is z. So I can use Pythagoras' theorem with these quantities. So by Pythagoras, we have x plus y all squared plus 80 squared equals z squared. That's the relationship we're going to use. So now, you move on to step 5. What is step 5? Differentiate with respect to t. What's the derivative of this with respect to t?
2x plus 5. Derivative of x and y.
160.
Derivative of x is
dx and
dx dt, right? Remember, it's not just 1 now because t is the real independent variable. Plus dy dt, right? We got this from the chain rule, by the way. Derivative of this?
160.
0. It's a constant. Derivative of this?
2z.
That's implicit differentiation with respect to t. Now, this is the guy I want to find, right? X and y I already know. Dy dt, dx dt and dy dt I already know. What about z? We need z. How do we find it?
Divided by 2z.
Huh? Go back to the equation, right? So this is actually written on the handout, right? There comes a time when you want to plug stuff in, but you don't have all the information. Whenever there's information missing, you'll go back to the equations that you set up before. Now, because I know x and y, I can plug them into this equation and just solve for the z. So go back to 4. And so I'm going to plug them in. My x is 20 and my y is 40. Okay, so what's that?
100.
Huh?
100.
Z is 100? How'd you get that?
So 3, 4, 5 times.
So 3, 4, 5. This guy here would be 60 squared plus 80 squared equals z squared. The 60 you can think of as 3 times 20. The 80 you can think of as 4 times 20. So the z must be 5 times 20 because it's a 3, 4, 5 triangle, right? The two sides are factors of 3 and 4. The hypotenuse must be a factor of 5, and so z equals 100. Or you could actually take these squares and subtract. Take a square root. Okay, so we have z equals 100. So now we can get to actually step 6, where we can plug in everything we know and solve for what we want to find. So I will plug. Right here, you could cancel the 2's. So I would plug in x plus y, which is 20 plus 40, times dx dt plus dy dt equals the z is 100 into z dt. So this is just 60 times 30 over 100 equals dz dt. So what is that? 18? 18 miles per hour is dz dt. I don't really care about the units, but it would be miles per hour. And I'll check that that's what I wanted to find, so we're good. Questions? Let's go with another situation. Example 5. So, step 1, read. A baseball diamond is a square with a side of 90 feet. A batter hits the ball and runs towards first base with a speed of 24 feet per second. Part A, at what rate is his distance from second base decreasing when he's halfway to first base? So 2, we're going to come up with a diagram. Right? The baseball diamond. So, what's the baseball diamond? He hits the ball here, and he starts to run towards first base, right? So then this guy's here at the moment. And now it says, at what rate is his distance from second base decreasing when he's halfway to first base? So what quantity are they actually asking us about? What represents his distance from second base? Huh? Like what? No, it says, at what rate is his distance from second base decreasing when he's halfway to first base? So what on this diagram is his distance to second base? A line from him to second, right? Distance is always measured in a straight line, right? Connecting the two things that you care about. Okay, so now that that's the picture, now we have to label it. How do we label it? Where would you label it?
Second and first is 90.
To first and second, that's what? It's 90, and it's always going to be 90. So I can label that with a constant. What else would you label?
First to batter is 45.
The first to batter is?
45.
It's not 45. Why is it not 45? Because he's actually running, he's moving, right? This is just a snapshot of one part of the situation, right? So this distance here, I call it something, x, because it's changing. What other distance do I care about? Well, the one that I was asked about would be a good one to label, right? The distance between the batter and second base. So we'll call that what? So that's my diagram. Now, of course, this is a square, which means that that is a right angle. That is my diagram. That is still appropriate. For step 4. Step 3, write down what we know, what we want to find. What do we know so far? Based on the variables that we have. We know dx dt, what's its value? No. Come again? No. No? What's going to happen to x in this picture as time goes on? It's going to decrease. So, what's dx dt? Minus 24. Because x is decreasing. You need that negative sign. Okay. Now, what do we want? dy dt. When do we want it? Now. When do we want it?
Halfway.
When the batter is halfway to first base, how do I describe that situation?
Half of 90.
What's a half of 90?
45.
Okay, but who's the 45? Who's the 45? X is the 45. Right? It says when he is halfway to first base, which means this is measuring his distance from first base. If he's halfway, that must be 45. So this is what I know. It has to be negative because it's decreasing. And this is what I want to find. And that's the conditions. So now the relationship, again, it's a right angle triangle. This shows up all the time. And so now we will have x squared plus 90 squared equals y squared. Step 5. What's step 5? Differentiate. What do we get?
dx dy
dx dt
plus 0.
plus 0
2y.
dy dt. Just cancel the 2's. And what I actually want to find is dy dt. So now I want to plug everything in and solve for what I want. The x, I know it's 45. Dx dt, I know is minus 24. The y is?
Unknown, we gotta put it back there.
Right, I don't know what the y is, so go back to step 4. So I'm going to plug in what I know. X is 45. Okay, what's y? It's not a special triangle. It's not a 3, 4, 5 or a 5, 12, 13. So just kind of have to do this the old-fashioned way. So 45 squared. The good thing about 90 is it's actually 2 times 45, which I'm going to take advantage of. So that means this is 4 times 45 squared. Which makes this side 5 times 45 squared. Which means my y is actually the square root of 45 squared times 5. Discrete or radical. And I would get 45 radical 5. Okay. So that's my y value. And now I can just plug in. This means step 6, my dy dt. X is 45 minus 24 for 45 radical 5. This is all multiplication, so I can cancel. So it's minus 24 over radical 5. And that would be in 3 perspective. So again, same process. Read the problem carefully, make sure you know what's going on. Draw a picture to describe what's going on if possible, or necessary, which usually will be necessary if they didn't give you an equation. Make sure you label things properly. Anything that's not changing, label with a constant. Anything that's changing, label with a variable. Write down what you know, write down what you want to find. Make sure that your rates, the sign actually matters. Use positive for something that's, if in your diagram the thing is increasing, you need a positive number. If your diagram the thing is decreasing, you need a negative number. Then you're going to set up an equation based on the diagram you just made. You can differentiate that equation with respect to t, and then you need to plug in what you want, what you know, and what you want to find. If you have something that is here that you don't actually know the value for, go back to step 4 and solve for it. And then at the end of the day, you'll get the answer. Hopefully you'll get the answer to what you want. And that's that. Any questions? Yeah. Oh, I wrote 90 as 2 times 45. And then I distributed the square because it's a product. Just, I know that a times b squared is just a squared b squared. So I did that here.
That wouldn't work if it's,
If it's a plus, I couldn't do it.
yeah.
Right. With multiplication, I can do that. Right? And so then I get to here, and then it's kind of like x plus 4x gives me 5x. I'm going to add the apples. So that's algebra. And then I take the square root. And it's also true that if I have the square root of two things, I can just take the square root of the individuals. And I get this. Part B is actually pretty similar. Things will just be set up slightly different. I want you guys to try that part. And maybe next time, if you have trouble with it, you can ask me at the beginning of class. Let's move on to problem 7. This is actually similar to a problem that was on a quiz. Superman is cruising at 390 feet per second at an altitude of 5,000 feet. He flies directly over Jhevon's house. Assuming Superman maintains altitude and speed, how fast is the distance from Jhevon's house to Superman changing at the time when Superman is 13,000 feet from Jhevon's house? Okay, so the first thing we're going to do is read, roll our eyes, that Jhevon put himself in his own crossing again, and then we go to the diagram. What's the diagram going to look like? This is the important part. Step 2 and 4 are like the real crucial parts. And you have to make sure you get those two right. The others are kind of like following your nose after a while. Okay, so here's the ground, and so I know that's just some height that I'm measuring into the air, and that's going to be 5,000, right? Now we're the question says assuming he maintains the altitude, right? Which means he's always flying at this level, which means this is not changing. I can label it with 5,000. I can label it a constant. Now let's say, assuming he's flying in that direction, I could have drawn it in that direction, it doesn't matter. Just make sure your labels are consistent with the values that you're plugging in. And let's just say, for the sake of argument, Jhevon's house is right here. Right? So he flies over. Okay. What do we want to measure?
From your house to where with the S.
Right. We're measuring the distance between two objects is just a straight line that connects the two objects. So I would. What?
What is that called? Like in science?
You can think of this as a displacement, yeah, or a vector or something like that. Right. I just know I'm pegging everything to the house and Superman. And then I can connect the distance he traveled away from the house to the altitude. So I have that. How do I label things?
The top of the altitude to the S, would that be the speed?
Right, it's changing. So I call it X because he's flying, right? He's maintaining his speed. So that's actually changing. What about this? It's also changing, right? Because the further he goes, the longer this would get. Right? So call that Y. The altitude isn't changing, so I'm going to leave that at 5,000. But again, I get a right triangle. Okay, now let's fill stuff in. What do we know? What do we want? What's okay? So what? Right. That's dx dt. That's the rate at which x is changing, and it's 390. It's positive 390 because according to my diagram, it would be increasing if he continues flying. Okay. What do I want? Well, dy dt. How fast is that distance changing? When?
When he's 13,000 feet.
Okay, so what's that describing?
X. And X equals to 2,000.
it says when Superman is 13,000 feet from the house. So you're going to measure the distance between Superman and the house, which is actually the y. And you want that to be 13,000. So what's the equation here? Pythagorean theorem again. X squared plus 5,000 squared is equal to y squared. So then
And what?
differentiate again, dy dt is what I want to find. Dx dt I know, y I know, x I don't know. So I need x. I'm going to go back to step 4. I'm going to solve for that x. And what is x going to be? So that x squared plus 5,000 squared equals 13,000 squared. Which means x is that's right, 12,000. Right? The two Pythagorean intervals you'll be tested on is 3, 4, 5. And then there's a 5, 12, 13. Right? So those three numbers will go together. If the hypotenuse is the largest one, then the other two, and you know one leg is one of them, the other two will be. So here it's just multiplying by 1,000 in each part. And that is right. So those numbers are numbers you're always looking for. Right? They're not always present, like in the last example, I actually had to solve it out, I got 45 radical 5. But you're always looking for these numbers to come together when you're in Pythagoras' theorem. So x is 12,000, and so now in step 6 I can just plug it in. dy dt equals x, which is 12,000, dx dt, which is 390, over y, which is 13,000. So it's 12 times 30. Per second. Any questions on that? So in the homeworks, you'll see a lot of varying situations, and there are more examples here for you to practice. I'm not going to do any more. Try them on your own, and if you have any questions, we can talk at the beginning of class. But I guess for the sake of focus, the kind of problems I put on a test is like problem 1, problem 3, problem 7. And on the more examples page, probably something like problem 1 or 2. It's good to practice all of them. That's how you get yourself in the groove of something. But you know, when it comes down to studying for a test and time is short, I focus on those and whatever I put in the review. So let's actually move on. That's all I wanted to do for related rates. So really related rates is just a matter of going through those 6 steps. There's nothing really. It's just the diagrams might change. You have to set up the diagram, and the equation might be different, things like that. But for the most part, this is the structure in which you're going to do these problems. If there are no questions, we'll move on to the next section. I don't think we'll get to curve sketching, but bring those handouts that I gave you next class. We'll start it. So what we're going to move on to now is 4.2. Maximum and minimum values. There are two kinds we'll care about. One is called absolute maximums and minimums. AKA, you might see them referred to as global maximums and minimums. The second type is called local maximums and minimums, AKA relative maximums and minimums. Also note, the word, let's mention the phrase, extreme point. May be used to describe max and min points. And extrema is the plural. So basically, if you see a phrase like local extrema, you can interpret that as local maximums and minimums. Right? They mean the same thing. So let's start with absolute maximums and minimums. I'm going to tell you what they are. Here's the definition. this is the definition of absolute max and min. Right? So you have some function on some domain. If you can find a point in that domain such that if you evaluate the function at that point, its y value will be greater than or equal to every other y value in that domain, then we call it an absolute max. An absolute max is the biggest guy around in general, in the world, right? That's why it's global, right? Look at the entire domain of the function that you're given. Who's the biggest y value? If that guy exists, that's called the absolute max. You can do this in the opposite way, and if you find the smallest guy around, in general, you call that the absolute min. Right? So it's absolute and it's global in the sense that you're looking on the entire domain. And as the name would suggest, local maximums and minimums are, you're not looking on the entire domain, you're just looking in a local area. So, how about local max and min? So again, D is the domain of F. If there is a C, and notice I'm saying if there is such a point. It means it doesn't have to exist. You don't have to have them. But if it's there, then this is the quality that you look for, such that f of c is greater than or equal to f of x for all x near c, then f of c is a local max. If f of c is less than or equal to f of x for all x near c, then f of c is a local minimum. And so the important part about local is it's only when you're near the point, meaning in some open interval around the point. So you just kind of zoom in on the point, look a little bit to your right and to your left, and if he's the biggest guy, you call him a local max. If he's the smallest guy in that small region, then you call him a local min. They don't have to exist, but they can. So let me give you some illustrations of what these guys are, and then I'll tell you how to calculate them, how to find them. For example, let's say this is your graph. there are a bunch of graphs. So what we're going to do is on these pictures, we're going to identify the absolute maximums and minimums and the local maximums and minimums. So you kind of see the ideas. These are shaded. Okay. On this picture, where do you think the absolute maximums and minimums are? Absolute max, I'll abbreviate AM. Absolute min. AM. Local max, LM. Local min. So don't have to write that down on there. Okay. Here, absolute max, absolute min, do they exist?
Yeah.
Right. There's a y value at this top here, at the peak, right? That guy here is an absolute max, right? Because if you look on the entire domain of this function, that y value is bigger than every other y value, right? What about absolute mins? Where? Where's the absolute min? The smallest y values are on.
Right there, where x equals 0.
Well, x not equals 0.
Y.
Y equals 0. Right, so this here, this is an absolute min. Right? This is also an absolute min. So you have two absolute mins here. By the way, if they're labeled like this is A and this is B and the x value for this is C, what you would say is f of C is an absolute max, f of B is an absolute min, and f of A is an absolute min. What about local? Do you have any local maximums here? It turns out that this absolute max is also a local max. Right? He's not only the biggest guy in general, but if you zoom in and only look at a small neighborhood surrounding him, he's also the biggest guy in that small neighborhood. So that's a local maximum. Right? Similarly with these guys, they're also local minimums, right? They're not only the smallest guys in general, but if you zoom in to some small neighborhood around them, they're the smallest guys in that neighborhood. So these are also local minimums. Okay, let's look at this guy. Do you have any absolute maximums? Is there any y value that's bigger than every other y value? Where would that be? This is a hole. What is right below the hole? There's no absolute maximum. There's no y value that's bigger than every other y value, right? This hole means it's a gap. It means you're approaching that position, but you can never get to it, right? And no matter what y value you pick, you can always get a y value that's closer to it, right? So there is actually no absolute max. Or in that regard, there's actually no local max either, right? There's no y value that if you zoom into his region, he's the biggest guy around.
Is that always true?
What?
If there's no absolute maximums and local maximum?
No. But we have a variety of situations here. We're going to see what they are, what the possibilities are. What about mins?
Yeah.
This guy, right? Does he exist? He is an absolute min, and he's also a local min. Local. Right? he's the smallest y value in general, and he's also the smallest y value if I zoom in. What about this one?
The absolute and the local is what is that?
This is absolute and local what?
Min.
This is absolute min and local min. Right. Where's the absolute max and local max?
Would it be infinity?
No, we describe them to be y values. They're actually finite numbers. So there's none. There's no absolute max. There's no local max. Okay. What about this one? Now it's getting complicated. Very cute.
The absolute minimum would be all the way down.
This guy here is the absolute minimum. Alright? And he's also a local minimum. Right?
Other local minimums would be that right
This
here,
one here is a local minimum.
and that right there. Where the
And
dot
right, where the dot is also a local minimum. Notice that these guys here, they're local minimums, but they're not absolute minimums, right? Because if you look at the whole picture, there's a y value that's smaller than them, right? But in their little neighborhood, they're the smallest people around. What about absolute max?
is the
top.
Dot at the top, absolute max. He's the biggest y value in this entire picture, right? Which, by definition, pretty much an absolute max is always going to be a local max. What about any local mins?
Min max.
Local max.
The two.
These two top of these hills, right? These are local maximums. They're not absolute maximums because they're not the biggest guys around, but in their region, they're at the top of the hill, right? So they're the biggest guys in their small neighborhood. This guy.
The absolute max is at the top.
The top here, that's going to be an absolute max. It's also a local max because if I zoom in, he's still the biggest. What about mins?
What is this?
There's no absolute min, there's no local min. Because it keeps going down, right? Whatever y value you tell me, eventually I can find a smaller y value. This one.
Absolute max would be the two top. Well, I don't know what's that.
There's no absolute max here, right? There's no y value that's bigger than every other y value.
But there's local those two, right? No,
This here is a local max.
and those two.
Is it?
Yeah.
It's not.
No, no.
Why is it not a local max?
Is there something
Because
here?
look at some small neighborhood on the x-axis here. Right? Now if you're in that neighborhood, right? See this y value here? He's not the biggest. Their y value is on this guy that's bigger than him. Right? No matter how small I go, there's always going to be y values that are bigger than him. But the thing is, they never actually reach a maximum. They keep getting bigger and bigger, but they never actually get to this destination. So these y values are larger, but they never actually get to be the largest. So there's no local max here,
And no local min.
and there's no local min there either. Here's a local max though, right? In that hill. This is a local max.
So there's a local min.
This is a local min.
Oh, there'll be no absolute min.
This is a local min, and there's no absolute min. Right? Because this keeps going down forever. There's no y value that's smaller than every other y value in the entire picture. This one.
Absolute min will be a problem.
This guy here is going to be an absolute min. He's also a local min.
There's no local min again.
Local min here,
And there.
local min here,
Absolute max is at the top.
absolute max is here.
And those are local.
He's also a local max.
The two parts are local max.
Two hubs here, local max, here's a local min, These are not absolute mins because this y value is bigger than them. What about this guy here? Nothing, because he never actually gets to that destination. And even in that region, these guys are still bigger. So that's the idea. Very typically in our examples, local maximums and minimums, they're actually going to be at the top of hills or at the smallest points in a valley.
Does that mean
Wow.
the previous one is also a local min between the local?
Yes, this here is a local. So with absolute, you're looking in general. With local, you're just looking in some small region on the x-axis. So that's how you can identify them on a picture. You'll know what they're like. This intuition is going to help you with curve sketching, but to actually compute things, we're not going to be using the pictures. We're going to be using the functions. So let's talk about how do we actually find these. Like if I give you a formula for a graph, how do you actually find these locations? Right? First, let's talk about two theorems that are important. There's a theorem called the extreme value theorem. So as you saw here, there are situations where we can have no absolute max or no absolute min or anything like that. But there's another situation in which we're guaranteed to have these. This is described by the extreme value theorem. This says if f of x is continuous, meaning you can draw it without lifting your pencil off the page, on a closed interval AB. That means you're looking at some portion of the domain where the endpoints are included. Then f of x must attain an absolute max or min. Meaning, once you're continuous on a closed interval, you're guaranteed to have an absolute max or min. Right? Once you can draw the function without lifting your pencil off the page, and you don't do something like approach an asymptote where you can't include the endpoints, you'll always be able to find something that's the biggest guy around or something that's the smallest guy around. So continuous functions on closed intervals, you will always be able to find absolute maximums and minimums. And there's going to be a problem on your test where you have to do that. I'll show you how to do that. Another important theorem is Fermat's theorem. Not to be confused with Fermat's last theorem, which Andrew Wiles proved recently, which has been unproven for like 3 centuries or whatever. Fermat's theorem is a guy that kind of helps us to classify in one direction local maximums and minimums. So it says the following. If f of x is continuous at x equals c, and f prime of x exists at x equals c, then, right, so my function is continuous at this point, and I know the derivative exists. I actually don't know the derivative exists. The derivative doesn't have to exist. So assuming f is continuous at x equals c, and f of c is a max or min So here's a theorem that tells us if we have a max and the derivative exists, then the derivative will be 0. The same is true for minimums. So something like, if your function looks like this at the top of a hill, right? Your derivative will exist here and the slope will be 0, right? Or you could be at the bottom of something like this, right? So if you're a maximum or a minimum and your derivative exists at the point, then it must be 0.
Is that for all maximum and minimums?
It's not for all maximums and minimums. It's, in this situation, you know that that must be true. It doesn't work backwards. It does not work backwards. i.e., just because f prime is 0, it does not mean you have a maximum or a minimum. Example. Y equals x cubed is an example of that. If you take the y prime, you get 3x squared. Note, when x equals 0, y prime equals 0, the derivative is 0 at x equals 0. But if you know the graph of y equals x cubed, at 0, you don't have a maximum or a minimum. Right? So it doesn't work backwards. Right? That reason is why we're going to have things like the first derivative test and second derivative test. Also, note that we can have maximums or minimums if f prime does not exist. So an example there would be y equals the absolute value of x. At x equals 0, you have a minimum, but we already know that the derivative doesn't actually exist there. For these reasons, we need to develop tests to find maximums and minimums. Okay. So we're going to be doing a couple methods here, well, about 3 methods. So let's deal with this situation, finding absolute max min on closed intervals. What we use here is called the closed interval method. Step 1 in the closed interval method. Call the interval a, b. So if I give you a closed interval and I give you a function, I say find the absolute maximums and minimums on this interval. You will always do this process. The first thing you're going to do is you're going to find f prime I kind of have to define curve points. And find the critical points of f that are in AB. I'll tell you what the critical points are. That's a very special phrase. evaluate f at the endpoints. I.e., you're going to find f of a and f of b 3 And at the end of the day, you're going to compare this. What? What did you say? What happened? Oh, no. Fat. Evaluate fat. No, evaluate f at the endpoints. Right? That means you're going to find f at the left endpoint and f at the right endpoint. You're finding all these y values, and you want to see who's the biggest and who's the smallest. So that's the important thing at the end of the day. So we know critical numbers. There are two situations that we know nicely it fits in with absolute max or min. If we know that the derivative is 0, that will give us a max or a min. But we also know cases where the derivative is undefined and it will give us a max or min, as in the case of sharp corners. Right? So those are two situations that we're always going to look for. Right? Or if you just have something with one side to it, then the derivative is not going to exist because the limit won't exist. So we realize that these guys are situations where we can find absolute maximum, where we can find maximums and minimums. So we're going to find the critical numbers. It's going to be where the derivative is 0 or undefined. Right, so the first thing you're going to do is you're going to find the critical points. Of course, critical number, the critical point will be just the x value and the y value. X comma f of x is called the critical point. So I'm going to find all the critical points. So I'm going to go through, I'm going to find all the points on f where the derivative is 0 or undefined. I'm going to evaluate all the y values. Then I'm going to evaluate the y values at the endpoints. Then I'm going to compare them. I'm going to say who's the biggest y value, who's the smallest y value. Example.
What happens if you have two critical points?
If you have what?
Two critical points.
You can have many, but it doesn't matter. I'm going to still pick out the largest or the smallest for absolute maximum. I only care about the biggest and the smallest. And there could be several guys who are bigger, who are the biggest or the smallest. Here, let's continue with this one. right? So a problem like this will show up on the test and on the final. It'll usually be like part A of a problem or something like that. Right? So you're just going to be given a function, you're going to be given a closed interval, and you're going to be asked to find the absolute maximum or minimum on that interval. The extreme value theorem says we are guaranteed to be able to find these if the function is continuous. This is a polynomial, it's continuous. Right? So I know that these points actually exist, so now I actually want to find them. What we're going to do is we're going to use the closed interval method. So step one is we need to find the critical points. So for critical points, remember that f prime equals 0 or undefined. So what I'm going to do is I'm going to find f prime, which is right. Now set that equal to 0 for critical points. Notice it's never undefined because it is also a polynomial. Right? So the derivative is this expression. It's never undefined, so I don't have to check for that. But I can set it to 0 to try to see if I can find x values. So what would be the x values here? I can take out a 4x. Minus. So x equals 4, or x equals radical 2, or x equals minus radical 2. Right? So these are values that make the derivative 0 or undefined. Right? X equals 0, x equals radical 2, x equals minus radical 2. Now, one thing you always have to check is you have to check that these are present in the interval that you're considering. Right? So is 0 in this interval? Yes. Right? Is radical 2 in this interval? Yes, because radical 2 is like 1.417. Is minus 2 radical 2 in this interval? Yes. Right? In fact, let's make it nicer. Make that minus 1. And so now you realize that this guy is not in. Right? I want to show you that not everything you find, you just run with it. Right? You have to check. So this guy you would reject. Note, x equals minus radical 2 is not in the interval minus 1 to 3, so reject. Otherwise, what we're going to do is we're going to find f evaluated at these values. Find f of 0, which is going to be 0. Find f of radical 2 is the other guy, which is going to be. Throw in a radical 2 here, what do you get?
2 or 4.
You get 4. Put in a radical 2 here. So you get 4 minus 8, you get negative 4. Right? And those are the only 2 points to test. So that was step 1. Find the critical points, look at who is it actually in your interval, and find the y values at those points. 2. We're going to do what we call test the endpoints. Meaning, you're going to go to the endpoints. You're going to find f of a and f of b. So I'm simply going to find f of minus 1, and I'm going to find f of 3. So if I put in minus 1 here, I get what? I get minus 3. If I plug in 3, what do I get? If I plug in 3, what do I get?
What are you putting in 3?
Into f. I'm finding f. Yes, the original.
Oh.
So 3 to the 4th is? That's 81 minus 81 minus what? Okay, and so that gives us. You guys are falling asleep on me. Okay, so now the last step, right? So first step, find the critical points, test the ones that are in the interval in the original function. Then you test the endpoints of the interval in the original function. And then 3, you compare. Meaning, I want the absolute max and the absolute min, which means the absolute max is the biggest guy around. Who's the absolute max? F of 3. The value I get there is 45. That's bigger than everyone else. F of 3 equals 45 is the absolute max. He is the biggest y value around. Absolute min. F of radical 2, he's minus 4. That's the smallest value around. That's going to be the process. The problem is always going to look like this. You're going to be given a function, given an interval, find the absolute max and min. And if you're asked for the absolute max and min, there's a different process for local maximums and minimums. But if you're trying for absolute max and mins, find the critical points, make sure that they exist in your interval, plug them into the original function.
Yeah, we get it.
What?
You ask for -2.
On your left.
Is it right?
Where?
On your left, number 3.
We're
Compare.
compare.
Should be radical 2.
Radical 2. Yes.
Oh, so this is
So, yeah, so the first thing you do is you find the critical points, figure out which ones are in the interval, test those points in the original function. Then you test the endpoints, right? These guys that you're given, test those in the original function. At the end of the day, you're going to have a bunch of y values. Take the biggest one, that's your absolute max. Take the smallest one, that's your absolute min. For the last few minutes, we're going to be doing this in more detail in the next class. For the last few minutes, let's just kind of look at what the picture would look like here. What are we actually talking about? It's 4 minus 4x squared. So we're going to be learning to graph things in this class, which is what curve sketching is about. It's about sketching curves. And one of the ways we're going to do this is, first, notice that we're going to, if you found f prime, which we already did, that's 4x cubed minus 4 minus 8x. Right? And then you found the critical points, which we already did. Now the critical points in this case is where the derivative was 0. Right? This was x was 0, x was minus radical 2, x was positive radical 2. Now look at what's happening. If I actually put these on a number line and I test them in the first derivative, right? So I put my 0 here, put my minus radical 2 here, put my positive radical 2 here, right? Now you were doing some things like this in the homework, that you'll remember to extend. If you plug in values in between these, right? Like pick a random value here, what would you try? -2 is over there. You can try a -1, try a 1, and try a 2. Right. Now if I plug these guys into the first derivative, which I could have written as this, right? So if I plug a -2 into here, right, this would be a negative. That would be a positive. So I would get a negative here, right? Now remember in the first derivative, what is the interpretation of negative? I mean it's decreasing, right? So the curve looks like that. If I plug in a -1, this will be negative, that will be negative, negative times negative is positive, so in this region it's positive, which means increasing. If I plug in a 1 into this, that's positive, that's negative, positive times negative is negative, and the curve is decreasing here. Plug in a 2, positive, positive, multiplication is positive, you're increasing here. Now notice this is a polynomial, so the function is continuous, it exists everywhere. Meaning, if I'm decreasing and then increasing, and I exist at this point, what is this point? It has to be a minimum. In fact, it's a local minimum. What about 0? That has to be a maximum. In fact, it's a local maximum, because I increase and then decrease, and I exist at 0. This one will be a minimum. Right? So this is just a slight preview of one of the parts that you're going to be doing in curve sketching. I'm not going to get super detailed here. But when you start to look at this, now you can actually draw the picture and see what we were talking about. So we actually tested the point here. We know that this point was radical 2 comma, when f of radical 2 was what? Was minus 4? Notice that f of minus radical 2 will also be minus 4. F of 0 was 0. So I've actually found some minimum points here. This is minus radical 2, minus 4. Positive radical 2, minus 4. This is 0, comma 0. I know that this is a maximum. I know that these are minimums. Right? So it's kind of like I can find the vertex of something that's not a quadratic. Now, you can plug in numbers over here to figure out how your function behaves. But we know it's a x to the 4th graph, so I know it's like the right side and the left side is going out to infinity. So the thing is, the graph has to come down here to pass through that point, right? It has to turn to come up to hit that maximum. It has to turn around to come back and hit this point. And it has to turn around here to continue its behavior. Right? So this graph actually looks like a W. Yeah.
When we don't know that, right? Like the homework, for example.
Oh, we're always going to be able to do this.
But
You'll plug in a point.
What do we have to do with concavity? Like the second derivative?
Yeah, that's later. That's later. That's more advanced. Right. Okay, so that would be what the whole graph looks like, right? Now notice that these guys are absolute minimums, but we didn't have the whole graph. What did we have? We have from minus 1, right, to what? To 3. So we kind of ignored everything else. So in other words, we were dealing with this picture. And the question was, who's the absolute max and who's the absolute min? Now from the picture you can see that this is the absolute min, right? It's the smallest guy around. This is the absolute max, that's going to be 3, comma 45. Right? Now this is a local max, but that's not what we were asked for. Right? So, but by the closed interval method, we could figure out that that was the absolute max when we're on the closed interval. Yeah, we'll talk about concavity. Like concavity is talking about how this thing is shaped, right? So the fact that this is shaped like a frowny face, we actually mentioned that was concave down before, and so on and so forth. But that's kind of an idea of where we're going, why we care about this stuff. It's about graphs and analyzing them. We'll stop there for now. I will see you guys on Monday. Yeah.